So we'll start from the very basic of quantum mechanics. Now for this we have to understand classical mechanics first versus the quantum mechanics. So now if we think in classical mechanics, what happens? If you throw a daily object like a cricket ball, you have a precise trajectory where to throw it. But in quantum mechanics, we are dealing with particles which are very small in size, that is they are microscopic in nature. So if you throw an electron to a specified position, it will have very less probability to reach 100% at that position. It may enter in many different directions. So this is the basic difference between classical mechanics and quantum mechanics. It says that the trajectory in classical mechanics is precise, the trajectory in quantum mechanics is uncertain. So this is the basic difference between quantum mechanics and classical mechanics. Now let us start with some drawbacks of classical mechanics. First of all, when we deal with a particular phenomenon called black body radiation, what happens is that if you get, this is let us say wavelength, this is let us say the energy density. Now if we do the experiment using a black body, first of all, what is black body? Black body is just an object with a very tiny hole, so that it can enter or it can absorb all the electromagnetic radiation, but when you heat it, it will start emitting the radiation. So higher the energy, higher the amount of heating, higher will be the energy output. And that's why if you take an iron rod and if you just start heating it, it becomes red. Now if you heat it more, it becomes white. That means it can radiate high energy frequencies or low wavelengths. So if we plot this experimental curve, we will see that the curve looks like this. If we take at higher temperature, the curve will look like this. That means with increase in temperature, the curve moves towards lower wavelength, means higher energy. So this created a problem among physicists, and then first Rayleigh and Jeans tried to explain the phenomenon using classical mechanics, and they started with classical mechanics and they used equipartition principle. So when they used equipartition principle, and they thought that energy is distributed in all three dimensions and each dimension carries an energy of half kT, where k is your Boltzmann constant. Using this concept, they arrived at an energy expression like dE equal to rho into d lambda, where they thought that rho is nothing but 8 pi kT by lambda to the power 4. So this equation, if we put that equation where k is your Boltzmann constant, T is the temperature, lambda is the wavelength. So if we plot this is rho, this is let us say this. If we plot this, you will get a good curve like this. So at higher wavelength side, it matches with the experimental curve. But the problem is that if we just think it logically, what happens is that if you see this curve is going upward without crossing any energy maximum. So what does it actually predicts? It predicts that whenever your lambda is high, it has a good match, but when your lambda is low, the match is not that good. So it predicts that all vibrations are equally excited, and it will create all particles into random motion, and as a result all particles will be excited to the same extent. So now if we think about this equation, if we see dE equal to rho into d lambda, where rho is nothing but 8 pi kt by lambda to the power 5. If you see, if we decrease lambda, then rho becomes maximum. So it crosses, this is the actual experimental curve. It goes like this without coming backward. So that means without having a maximum. So according to this theory, all vibrations, like all frequencies like ultraviolet, X-ray, gamma ray, everything will be excited at the same temperature. That means that it will create a phenomenon called ultraviolet catastrophe. So it means that at low temperature or even at room temperature, all frequencies will be excited and we will have no darkness, whatever may be the temperature. So according to this classical mechanics, there should not be any darkness. So this cannot happen. That means there is a drawback in the classical description of black body radiation. Then Max Planck came and he said that all frequencies are not excited, some discrete frequencies are excited according to the excitation source. So he proposed that the energy will be nothing but a multiple of nh nu, where n he proposed as maybe 0, 1, 2, 3, all these are discrete numbers. So this is called the quantization of energy. So using this quantization energy, and we should remember that he applied thermodynamics to arrive at this conclusion. So when he concluded using this quantization of energy, he predicted the equation like this: dE rho into d lambda, where rho is nothing but 8 pi hc by lambda to the power 5 e to the power hc by lambda kt minus 1. Now you see, with decrease in wavelength, lambda increases, but it again comes back at lower wavelength. So this, the experimental curve and the predicted curve by Max Planck is almost matching in shape. However, the problem is that still the best fit is not observed. So in the original theory, Max Planck never got the value of h. What he did just varied the value of h, and ultimately when he comes to 6.02 into 10 to the power 10 to the power minus 31 joule into second, when he arrived at this value, he found that the match becomes exactly similar, and that from then we know the value of h as Planck's constant. So this is a revolutionary theory which predicted that Planck's equation can easily describe the black body radiation. Now, in another case like heat capacity, where Dulong and Petit predicted that heat capacity of monoatomic solids will be thrice R. Okay. Now they used same equipartition principle and said that a monoatomic gas in one dimension will have an energy of kT. So since a monoatomic gas can move in 3 dimensions, the total energy will be thrice kT, is nothing but thrice Avogadro's number NaRT. Now we know that this is the internal energy. So this is the internal energy of a monoatomic gas. Now we know that heat capacity at constant volume is nothing but derivative of internal energy with respect to constant volume with respect to temperature at constant volume. So this will turn out to be thrice R. Okay, since n and n is a constant, so this will become equal to thrice R. Now if we know the value of thrice R, it will turn out to be almost close to 25 kilojoule per mole. But when new modern refrigeration technique came, it showed that we can go much lower temperature, and when they went to much lower temperature, they found that the heat capacity of a monoatomic gas is quite less than 25 kilojoule per mole. So it indicates that at low temperature, most of the oscillators remain silent. Some of the oscillators which had sufficient energy at that temperature are excited, and as a result heat capacity lows down. So this was a breakthrough by Einstein, and he proposed a new heat capacity equation based on temperature. So this is the difference between or this is the drawbacks of classical mechanics and advantages or fruitfulness or the beautifulness of quantum mechanics, which can explain those phenomena. And lastly, we know that if we take atomic spectra, the spectral lines are separated, not continuous, they are separated. So there is a distinct gap between this. So this, according to Planck's quantum equation, we know that E equal to h nu. So depending on the value of n, we can write h nu. So depending on the energy change, we have a particular value of frequency. Now these are the particular values of frequencies, and these frequencies are separated. That means the quantization of energy has taken place, and the lines are discrete, not continuous. So this is an experimental direct proof of the phenomenon called quantization.